This video is going to cover section 1.6 Chemical Equilibria of AQA A-Level Chemistry, focusing on calculations using Kc. This video will cover a recap of Kc expressions and units, deducing quantities at equilibrium, and quadratic equations in Kc calculations. Some calculations for Kc are fairly straightforward. For example, calculate Kc for the reaction given. At equilibrium, the concentrations were A equals 1.00 moles per decimeter cubed, B equals 1.50 moles per decimeter cubed, and C equals 0.500 moles per decimeter cubed. And the reaction is A plus 2B in equilibrium with C. Now for this, it is, as I said, fairly straightforward. We've been given the concentrations at equilibrium. We've been told that the concentration of A is 1 molar, B is 1.5, and C is 0.5. And we know that we're at equilibrium. We've also been given concentrations. So we can go straight into doing a Kc calculation with this one. So the first thing we need is the Kc expression. So concentration of products over reactants. Concentration in square brackets, remember. The products is C, so we have square brackets C divided by square brackets A times square brackets B, and B is squared. Now the B is squared because the stoichiometric ratio of B in the equation is 2. The others all have a stoichiometry of 1, which means that really these are C to the power of 1, A to the power of 1. But we don't need to worry about that, because when it's a 1, we can just ignore it. Now because we've got concentrations already, we can put these concentrations straight into this calculation. The concentration of C is 0.5, the concentration of A is 1, and the concentration of B is 1.5. It's 1.5 squared because of the stoichiometry. Now if we put that into our calculator, we get an answer of 0.222. Now I'm putting that to 3 significant figures because everything in the question has been given to 3 significant figures. It's not absolutely necessary to do that when you're in a chemistry exam, unless they tell you give your answer to the appropriate degree of precision. You have to be able to look at the question and work that out. But 3 significant figures is always a good bet if they don't tell you what to use. Now, the other thing we have to remember is if we're looking at Kc, we do need to make sure that we've got units. Now we've got here one concentration term on the top of the calculation because we have C on the top, so we have 1 mole per decimeter cubed on the top, and on the bottom we've actually got moles per decimeter cubed for A, and then we have moles per decimeter cubed squared for B. Now the moles per decimeter cubed can cancel out one of the ones on the bottom, so we get left with 1 over moles squared dm minus 6. Now if you remember that when we have indices outside of a bracket, minus 3 is times by 2 to give us what the total indices would be. So it would be moles 1 times 2 would be moles 2, and the minus 3 for the dm is times by 2 to get dm minus 6. And as we looked at in the previous video, to get rid of this fraction, we invert these values and we invert the power, we invert the indices as well. So the moles plus 2 becomes moles minus 2, and the dm minus 6 becomes dm plus 6, and that's the unit. So the answer here would be 0.222 moles minus 2 dm plus 6. So as I said, that's a fairly straightforward Kc calculation. A way of making that slightly more difficult would be, instead of giving you concentrations, the question gave you moles only and then a volume. Now if they give you moles and a volume, you can calculate the concentration and proceed exactly the same as before if you're told it is at equilibrium. A more difficult type of Kc calculation involves being given a mixture of initial and equilibrium quantities, almost always normally moles. This mixture of data, the initial and equilibrium quantities, is used to find all of the equilibrium quantities. And one method of doing this is to use something called an ice table. And I'm going to go through showing you how to use the ICE table, but just to introduce this to you to begin with. This is just a method of working. This is not something that's absolutely expected of you in the exam, but it is the most common way of calculating these. So ICE, it's just a way of remembering initial, change, and equilibrium. And I, C, and E all refer to number of moles. Now, if we had the equation AA plus BB in equilibrium with CC and DD, we'd set up an ICE table that looks a bit like this, in order of the reaction, with the reactants on the left and the products on the right. And when you're given the data in the question, you fill in the table with the data that you're given. So we're going to have a look at an example. 4 moles of ethanol and 4 moles of ethanoic acid are mixed and left to come to equilibrium, at which point 0.5 moles of ethanoic acid remain in solution. What is the value of Kc? So we know that we've got to go through and find out all of our values of the equilibrium quantities of our reactants and products. And we've got to have a think about what information we have. Well, the first thing we're going to do is we're going to build an ICE table. So there's an empty ICE table. I've put them in order of the chemicals and just put the names underneath instead. So we have ethanol, ethanoic acid, ethyl ethanoate and water in the same order as in the balanced chemical equation. It's also worth putting in the stoichiometry. These are all 1 to 1 to 1 to 1. So this is the ratio, which you don't have to put in, but it's helpful. Now, if we read through the question, we can see that we had 4 moles of ethanol and 4 moles of ethanoic acid are mixed. So I'm going to fill the table in. Initially, we had 4 moles of ethanol and 4 moles of ethanoic acid. They're mixed and left to come to equilibrium, at which point 0.5 moles of ethanoic acid remain in solution. So at equilibrium, we have 0.5 moles of ethanoic acid. Now that's all of the data from the table, but we can deduce some of the others. The reactants are mixed together. At the very start, when we have 4 moles of ethanol and 4 moles of ethanoic acid, we will have 0 moles of the products at the very beginning of the reaction. So we can put 0 for ethyl ethanoate and water for the initial moles, because there's none of that at the start. Then the other thing that we can do is we can work out by how much the ethanoic acid has changed, because we've got the initial moles and we have the equilibrium moles. Ethanoic acid's moles has decreased by 3.5. It's gone down by 3.5 moles. That's how many moles of ethanoic acid has reacted. Now, if we use our stoichiometric ratio that we've put in the table just here, if we know how much one species has reacted by, we can work out by how much all of the others have reacted. If 3.5 moles of ethanoic acid reacted, because it's a 1-to-1 ratio with ethanol, then we must also be able to say that ethanoic acid reacted 3.5 moles, ethanol has to react with 3.5 moles as well. I apologise, I didn't say that very well. But because it's 1-to-1, the same number of moles of each has to react. Looking at it to the products, if 3.5 moles of ethanoic acid has reacted, then because it's a 1-to-1 ratio with the products, ethyl ethanoate must have gone up by the same amount. So if 3.5 moles of ethanoic acid has reacted, we must have formed 3.5 moles of ethyl ethanoate. And because it's 1-to-1 with water as well, this will go up by 3.5 as well. This change row here always matches the stoichiometry, and that is really important. So it always has to match the ratio of the equation. Really, really important, that row. Only that row. The initial and the equilibrium do not have to be in that ratio, but the change row always has to match the stoichiometric ratio of the equation. And the reactants will always decrease and the products will always increase because we're using the reactants and we're producing the products. So at equilibrium, we can now work out our quantities. We started off with 4 moles of ethanol, but 3.5 moles have reacted, so there will be 0.5 moles of ethanol left at equilibrium. And ethyl ethanoate, we started off with 0, it's increased by 3.5, so at equilibrium we will have 3.5 moles, and the same for water. So those are our equilibrium quantities. Now the question asks, what is the value of Kc? So we need a Kc expression. Kc is going to be ethyl ethanoate, which I'm going to write in shorthand. If you're not asked for the expression, you don't have to worry about writing out in full. So I'm going to do a little bit of cheating here. Remember, if you're asked for the expression, you have to give the full formulae though. So products over reactants. I'm just going to put ethanoic there. Ooh, and I just did the wrong thing there. Remember, you have to use square brackets, not round brackets. So they can be a little bit wobbly, but they must be square. Now, the other thing to then think is that Kc is the equilibrium constant for concentration, and we have been given moles. So our values that we've worked out are moles. Now, if you look at this question, you might notice we have not been given a volume. But it doesn't actually matter for this one. Our concentrations will be moles over volume. If we were to say the volume is V, each of these, the concentration would be the moles we've worked out divided by V. Apologies for the mistakes. So they're the concentrations. Now if we pop those into our Kc expression, 3.5 divided by V will be the concentration of ethyl ethanoate, times by the concentration of water, which will be 3.5 divided by V, all divided by the ethanol, which is 0.5 divided by V for its concentration, and 0.5 divided by V for ethanoic acid. Now because the stoichiometry is the same on both sides of this equation, we have 2 moles of substance on the left and we have 2 moles on the right, we won't have any units, but it also does something very clever with the volumes as well. Only if the stoichiometry is equal, and only if we would have no units overall, can we cancel out the volumes. We have 2 lots of divide by V on the top of the equation, and we have 2 lots of divide by V on the bottom. But as I said, we can only do that if we have equal stoichiometry on both sides of the balanced equation. So we can simplify this to 3.5 squared divided by 0.5 squared, and if you put that into the calculator, that comes out to be 49, and there will be no units. So to look at a second example, just to make sure that you've got some experience of these, 1 mole of N2 and 2 moles of H2 were mixed and left to come to equilibrium, at which point 0.5 moles of N2 remained. What is the value of Kc for the reaction? Volume equals 0.5 decimeters cubed. N2 plus 3H2 in equilibrium with 2NH3. Again, this is our familiar reaction. It does come to equilibrium. It is a very common one. They use it a lot in exams, and also because it has a ratio. The ratio is not quite so nice. So we're going to have a look at this for 2 reasons. One, because we've now got a ratio, which means that the ice table becomes a little bit more complicated, and we've also got a volume here of 0.5 decimeters cubed with a reaction that doesn't have equal stoichiometry. So we do have to calculate concentrations here. So just to have a look through the question, we have 1 mole of N2 reacting with 2 moles of H2. It's left to come to equilibrium, and at equilibrium we have 0.5 moles of N2 remaining. And it's asking us to calculate the value of Kc. So what do we need? The first thing we're going to do is we're going to have a little ice table. So you can see how I've put the ice table down. You could obviously sketch it out. You'll get space to do working and exam paper. Now I've got N2, 3H2 and 2NH3 in the table. Now I've put a thick line to show the difference between the reactants and products. You don't have to do that if you don't want to. Some people like to do a double line, some people just do a single line. And in fact, if you're doing working, you can just leave it as you don't even need to put the lines. It's completely up to you, because this is just a method for doing the calculation. It's not necessary. So let's fill in the information that we have from the question. So it says 1 mole of N2. So we put a 1 there. It tells us that we have 2 moles of H2. Now the fact that it's 3H2 in the calculation doesn't affect how many moles we have. So we do just put 2 in there. Now these are mixed and left to come to equilibrium. And at that point we have 0.5 moles of N2 remaining. So that's all of the information in the question. What else can we fill in? Well, we're always going to have, unless told otherwise, 0 moles of the product initially. So we can put that in. And then we can start to use the values that we have. The N2 has decreased by 0.5 because we started off with 1 and then 0.5 moles remain at equilibrium. So that has decreased by 0.5. Now, if 0.5 moles of N has reacted, how much H2 would we need to react with the N2? Well, because this is a 1 to 3 ratio, we would need 1.5 moles of H2 to react with the 0.5 moles of H2. So the H2 is going to decrease by 1.5 because 0.5 and 1.5 are a 1 to 3 ratio, matching the stoichiometry of the equation. Then we can look at the NH3. Again, if 0.5 moles of N2 react, how much NH3 are we going to make? Well, this is a 1 to 2 ratio. So however much N2 reacts, we're going to make twice as much NH3. So the NH3 goes up by 1. So 0.5 to 1.5 to 1 as a whole number ratio is 1 to 3 to 2, remembering that this has to match the ratio of the equation, always. Now that we've got that filled in, we can work out the missing bits of the table. So H2 at equilibrium, 2 minus 1.5 means that we will have 0.5 left at equilibrium as well of H2, and we're going to make 1 mole of NH3, 1 mole of ammonia. Now we're being asked for Kc, and Kc is, as we've said before, concentrations. So the expression is going to be NH3 squared, because that's the products and it's a stoichiometry of 2, divided by N2 to the power of 1, times by H2 to the power of 3. Now these are concentrations, and at the minute we have moles in this table. We were given moles in the question. So we've got to turn these moles into concentration, and you can do that in the calculation in the Kc, or you can add a bit to your table. There's a variety of ways of doing this. So concentration is moles over volume. So I'm just going to add this to the table. So N2's concentration is going to be 0.5 divided by 0.5 because we have the volume at 0.5 in the question. So the concentration is going to be 1 for N2. It's going to be 1 for H2 because it's 0.5 divided by 0.5. And then for NH3 it's going to be 1 divided by 0.5, 1 moles divided by 0.5 decimeter cubed. So we'll have 2 mole per decimeter cubed of NH3 equilibrium. So remember, those are concentrations, so the units of those would be moles per decimeter cubed. Now that we've got concentrations, we can carry on as we did with our initial early example of putting the concentrations straight into Kc. So NH3's concentration is 2, so it's going to be 2, and that is squared because we have NH3 squared in the expression. That's going to be divided by the concentration of N2, which we've said is 1, and then we're going to times that by the concentration of H2, which is 1 cubed. Now 1 cubed is 1, 1 times 1 cubed is 1, so our Kc is just going to be 2 squared, or 4, and that's going to be our value. Now, as we've looked at in previous examples, the units for this Kc would be moles minus 2 dm plus 6. That's because we've got 2 concentration terms on the top and we have 4 on the bottom. So we end up with 2 concentration terms on the bottom, and that is moles minus 2 dm plus 6. But that's that example. The main things to remember, as I said, it is this ratio in the change row of the table does have to equal the ratio in the stoichiometric ratio of the equation. So activity 1, time for you to have a go. For each reaction given, work out how many moles will be present at equilibrium and calculate Kc with units. So exactly the same as the previous 2 examples. What we've got here are 3 equations. I've given you the ice tables already, so you don't have to worry about filling those in. You can add lines if you want when you copy these out. I've given you volumes for each scenario. You might find that you don't need to use the volume in the calculation like in the first example that I gave you, but if you're given a volume you can just calculate concentration anyway. So pause the video, and as always the answers will come next. Okay, let's have a look at activity 1 answers. Starting off with question 1. This is the hydrogen and iodine reaction again. As I said, it is very common. So looking at the ice table here, hydrogen we can see has an initial moles of 2, iodine initial moles of 2, and hydrogen iodide, because it is a product, initially there are 0 moles. You could get given moles initially and you just carry on as normal. Just when you work out your equilibrium, you take the initial moles of that into account. So anyway, the hydrogen starts off with 2 moles and at equilibrium we have 0.6. So the hydrogen has gone down by, helps if I have the pen on and not the highlighter, but hydrogen has gone down by 1.4 moles. 2 to 0.6 is minus 1.4. Now, if we look at the stoichiometric ratio, we have a ratio of 1 to 1 to 2 here. So our change row has also got to be in the ratio 1 to 1 to 2. If we have decreased the hydrogen by 1.4, then the iodine has to decrease by 1.4 as well, because it's a 1 to 1 ratio there. Now the hydrogen iodide has a stoichiometry of 2, so that is going to increase by 2.8, because that's twice 1.4. As I said, stoichiometry, the ratio has to equal the change ratio as well. So 1.4 to 1.4 to 2.8 is 1 to 1 to 2. Now don't let the minuses and pluses confuse you. Reactants will always decrease and products will always increase, because that's what happens in chemical reactions. So that's why H2 and I2 have a negative, and that's why the HI has a plus. So to work out equilibrium moles, we've already got that hydrogen is 0.6, because that's 2 minus 1.4. Iodine, 2 minus 1.4, is also going to be 0.6. And the hydrogen iodide is 0 plus 2.8, so at equilibrium we'll have 2.8 moles of that. So working out Kc then, Kc is the concentration of Hi squared, because the stoichiometry is 2, divided by the concentration of H2 times by the concentration of I2. Now, we look at this here, we've been given a volume of 1 decimeter cubed. Now, if you have a volume of 1 decimeter cubed, we know that concentration is moles over volume. Well, if our volume is 1, then concentration is moles over 1 decimeter cubed. In this case, concentration equals moles. So we don't actually have to do any calculations, we can go straight into doing this. The other way of looking at this is, on the left-hand side of the equation, we have 2 moles total, and on the right-hand side, we have 2 moles. So we have equal stoichiometry here as well. So our volumes will cancel out. Now, I'm going to do it that way. I'm going to do the volumes cancelling just to make sure that you've seen that as an example again. So concentration is moles over volume. So our hydrogen iodide is 2.8. That's the moles, divided by volume, which we can call V. That's all squared because it's Hi squared in the expression. Then we're going to divide that by the concentration of H2, which is 0.6 moles divided by the volume. And we're going to times that by the concentration of the iodine, which is also 0.6 moles over the volume. Now, just to go over this again, we've got 2 lots of divide by V on the top of this expression, because divide by V squared would be the same as divide by V divide by V. So our divide by V's can all cancel out on the top and the bottom, because there are 2 divide by V's on the top and there are 2 on the bottom. So our Kc is 2.8 squared divided by 0.6 squared. As I said, in this case particularly, concentration equals moles anyway because it's 1 decimeter cubed. But as I've said previously, if the stoichiometry is equal, then we can go down the route of cancelling out the V's. The examiners do need to see this though, so make sure that you show the examiner that you know that the volumes can cancel. Don't go straight into using the moles from the table here in your expression, because Kc is concentration and the ice table is almost always moles, and the examiners need to see that you are clear that you've got to turn your moles into a concentration before you can use them in Kc. So it seems like you're stating the obvious when you do stuff like divide by V and then cancel them out, but it's to show that you understand the chemistry. Anyway, if we were to solve this and work out the answer, we would get an answer of, if I put in the calculator, 2.8 squared divided by 0.6 squared, and that comes out to be 21.8. Now, there are no units, because we have equal stoichiometry, so 2 concentrations on the top and 2 concentrations on the bottom, but remember, just make sure you state no units. Question 2 for activity 2. All the information is given, as you can see here. So what we can do is we can say that the change in sulfur dioxide has gone down by 0.6, 1 to 0.4 is minus 0.6. Now we've got a stoichiometry of 2 to 1 to 2 across the equation here. So if 0.6 moles of SO2 has reacted, then there's only going to have been 0.3 moles of O2 reacting, because it's a 2 to 1 ratio. Now, how much SO3 is going to be produced? Well, it's a 2 to 2 ratio to SO2, or 1 to 1, so that is going to go up by 0.6. So again, check the ratio, 0.6, 0.3, 0.6, that is, in whole numbers, a 2 to 1 to 2 ratio. So at equilibrium, we would have 0.7 moles of O2 left, and we would have made 0.6 moles of SO3. Now, we do have to work out the concentrations for this, because we have a volume of 2 decimeters cubed, not 1, so we can't just say that moles and concentration are equal. And if we look across our equation, we've got 3 moles of reactant and 2 moles of product, so we can't cancel out our volumes in the Kc expression. So I am going to work out the concentration here. I'm going to put it at the bottom of my table. So 0.4 divided by 2, we have a concentration of 0.2. 0.7 divided by 2, we have a concentration of 0.35 at equilibrium, and 0.6 divided by 2, we would have a concentration of 0.3. The Kc expression is SO3 squared divided by SO2 squared times O2. That is a square bracket that would just be allowed. It is perhaps a little bit too round. Let's just change that. So I can put my values in here. So SO3 squared, so 0.3 squared, divided by SO2 squared, so 0.2 squared, times by 0.35. So putting that into the calculator, and we get an answer of 18.4. And looking at our units here, we've got 2 concentration terms on the top, and we have 2 on the bottom. So if we go with a highlighter here, the 2 here on the top will cancel out the 2 on the bottom, because both of these are squared, and so we have 1 concentration term left on the bottom. So moles per decimeter cubed becomes moles minus 1 dm plus 3, because if the moles per decimeter cubed is on the bottom, to bring it up to the top, we invert the powers. So moles minus 1 becomes moles plus 1, etc., etc. And that's the value of Kc. And number 3, we've got N2 plus 3H2 in equilibrium with 2NH3. Same old, we've seen this equation loads of times before. We have a volume of 0.5 decimeters cubed, and we can start to fill in our ice table. So this time we've been given an equilibrium value for the products, so we can say here that the NH3 has gone up by 0.4 from 0. Now we've got a ratio here of 1 to 3 to 2. So if 0.4 moles of NH3 has been formed, how much N2 must have been used? Well, that's a 2 to 1 ratio going in that direction, so we'd be dividing that by 2. So the N2 would have gone down by 0.2. 0.2 to 0.4 is the 1 to 2 ratio. Then looking from N2 to H2, we've got a 1 to 3 ratio, so however much N2, it will be times 3 for how much H2 has reacted. So if N2 has gone down by 0.2, then the H2 has gone down by 0.6. 0.2 to 0.6 to 0.4, that is our 1 to 3 to 2 ratio. So at equilibrium, how much do we have? Well, we have 1 minus 0.2, which is 0.8 moles of N2, and 1 minus 0.6, which is 0.4 moles of H2. We've been given a volume, we've worked out moles, so we now need to do concentration. So concentration is moles over volume. So 0.8 divided by 0.5, 0.4 divided by 0.5, and 0.4 divided by 0.5. So our concentrations are 1.6, 0.8, and 0.8. Our Kc expression, as we've done many times before, NH3 squared divided by N2 times H2 cubed, all in square brackets, and putting our values in 0.8 squared divided by 1.6 times 0.8 cubed, we come out with a value of 0.781, and the unit is moles minus 2 dm plus 6. So on to example 3, using Kc to determine moles. Now you could be asked to do this using the previous questions that we've been looking at, where you get given Kc and you're asked to work out an unknown equilibrium value, and that would just be a case of rearranging Kc to find that value. And I'm not going to go through an example on this video, although I can if you'd like me to. What we're going to look at is a slightly more advanced calculation for this. Now I would say if you found the previous ones difficult, to go back and have a look over those again before you move on to this one, if you did find those ones hard, because this one uses a bit more math skills from GCSE that you haven't used for a while. So we're going to have a look at an example and see what we can see. Given that Kc for the reaction is 4 at 25 degrees C, how much ethyl ethanoate will be formed when 2 moles of ethanoic acid and 2 moles of ethanol are mixed and allowed to reach equilibrium? Now we've been given Kc here, and we've been given some mole information. So the easiest thing to do for this is to go in with an ice table first of all, because once you've got your ice table and you go back through the question, you can see what information you have and what information you haven't. So there's my ice table, same as before, ethanol plus ethanoic acid forming ethyl ethanoate. You can make it a bit clearer that you have a line there between the reactants and products if you like, but you don't have to, just make it clearer. And we're going to read through the question again. Given that Kc for the reaction is 4, which I've written down already, how much ethyl ethanoate will be formed when 2 moles of ethanoic acid, and 2 moles of ethanol are mixed and allowed to reach equilibrium? Well, that's all of the information that we have. We've got Kc for the reaction is 4, which we've already written down. 25 degrees C doesn't mean anything unless you have a change of temperature. We've got 2 moles of ethanoic acid, which we've put in the table, and we have 2 moles of ethanol. So that's all of the information that we're given in the question. Can we fill anything else in on the table? Well, we know that our products are going to be 0, unless told otherwise, initially. And that's all that we've been given. So how do we proceed? Well, this is where we have to use a little bit of maths. In maths, if you have an unknown quantity, you would normally use an x, and that's what we're going to use here. We're going to say that x is how much ethanol has reacted by. So ethanol has decreased by minus x, or decreased by x. We're then going to look at the ratio in the question, or in the equation, excuse me, and we're going to say if x moles of ethanol has reacted, how much of ethanoic acid will react, and how much ethyl ethanoate and water will be formed. Now, because this is a 1:1:1:1 ratio, if x moles of ethanol has reacted, then x moles of ethanoic acid must also react, because they have to react in a 1:1 ratio. And if x moles of ethanol has reacted, x moles of ethyl ethanoate must be formed, and x moles of water, because remember the change row has to be the ratio of the equation. We don't know what those moles are, but we can say the ratio is going to be 1:1:1:1. So ethanol has decreased by x. So at equilibrium, there will be 2 minus x moles left. For ethanoic acid, there will be 2 minus x moles left. And how much ethyl ethanoate will we have at equilibrium? Well, we had 0 to begin with, and it's gone up by x. So we'll have x moles at equilibrium, and we'll have x moles of water. Now, this might look a little bit strange to begin with, but as I said, x is our unknown, and this bit is important. As long as we have the ratio of the equation in the change row of the table, then we're okay. So what can we do now? Well, we know our Kc expression. We know that Kc, as we've looked at before, is the concentration of the products over reactants. So we can put that into our table, or into our equation, sorry. Kc we've said is 4. The concentration of ethyl ethanoate will be X divided by the volume. That's going to be times by the concentration of the water, which is also going to be X moles, because that's how much we have at equilibrium, divided by whatever the volume is. There are our products, and we're going to divide those by the concentration of the reactants. So the concentration of ethanol will be 2 minus X divided by the volume, because that's the moles divided by volume, and the ethanoic acid is going to be the moles, 2 minus X, divided by the volume. Now, because we have equal stoichiometry on the left and right of the arrows, 2 moles on the left and 2 moles on the right, we have got our equation being balanced and equal with 2 volumes on the top and 2 volumes on the bottom. So I'm just going to tidy up the screen a little bit. There's the equation that we were just looking at. And as I was saying, because we've got divide by V times divide by V on the top, and we have divide by V times divide by V on the bottom, what we can do is we can cancel out the 2 divide by V's on the top. And so our expression simplifies to X squared, because X times X is X squared, divided by 2 minus X times 2 minus X. And what we're going to do is we're going to use a little bit of GCSE maths, and we're going to expand out this bracket. We're going to do this business from GCSE, if you remember. So what we're going to end up with is X squared on the top, and on the bottom we have 2 times 2, so we're going to have 4. We have 2 times minus X, so we're going to have minus 2X. And then on the left hand side we have minus X times 2, so we're going to have another minus 2X. And we have minus X times minus X, which is plus X squared. Now, we can't cancel out the X squareds on the top and on the bottom, because this is a plus X squared on the bottom of this equation. It's not a times X squared, so we can't cancel those out. What we have though is we now have an expression that is 4 on the left hand side, just here, equals X squared on the top, and then on the bottom we have 4 minus 4X, because we have minus 2X, which is minus 4X, plus X squared. Now what I'm going to do is I am going to times both sides by everything that's on the bottom of that fraction. Or the other way of looking at it is I'm going to bring everything that's on the bottom of that fraction and I'm going to move it to the other side. Now the cheats way of looking at rearranging equations is to say if you change the side, you change the sign. So everything in brackets at the minute is divide by on the right hand side. If I move that all to the left, it becomes times by. So we'd end up with 4 times 4 minus 4x plus x squared equals x squared. Now expanding that out again, we'd end up with 4 times 4, which is 16. 4 times minus 4x is minus 16x. 4 times x squared is plus 4x squared, all equals x squared. Now this might start to look a bit familiar, and what we can see here is we've got an x squared term, an x term, and a numerical term. And what we're actually going to have is a quadratic. Now quadratics need to be 0 equals, so what we're going to do is we're going to take this x squared, which is actually a plus x squared, and we're going to move it to the other side. So as I said, cheats way of rearranging is move it, change the side, change the sign, so our plus x squared becomes a minus x squared, and 4x squared minus x squared is 3x squared. So what we have here is a quadratic that is 3x squared minus 16x plus 16 equals 0. Now this is where the level 2 maths comes in for A-level sciences. There has to be a certain amount of GCSE level plus maths in the A-level sciences, and each of the A-level sciences, biology, chemistry and physics, has its own specific mathematical skills that you're expected to use from GCSE. Recognising and rearranging quadratic equations is one of those for A-level chemistry. How do we finish solving this? Well, again, just to tidy up the screen, I'm just going to put my quadratic equation up there. And how do we solve quadratics? Well, there are a few different ways, and it's up to you how you go about it. If you can solve the square, etc., then go for it. I've always been a fan of the quadratic formula, strange to say, but most people find that the easiest way to go through this calculation. So we've got here x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Now you do not get given that at A level. So if you remember it from GCSE, great. If you don't, then maybe go back and have a look at it. Anyway, what we need to do is label our quadratic, and the a term is always the number that comes before x squared, the b term is the number before the x, and the c term is just the number at the end. So we can put our numbers in, and we can see here that x is equal to minus b. So the minus b is minus 16, so this is going to be minus 16, plus or minus the square root of b squared, so minus 16 squared, minus 4 times a, which is 3, times c, which is 16, all divided by 2 times a, which is 3. Now, if we put some of this into our calculator, we're going to end up with minus 16 being plus 16, plus or minus the square root of 16 squared, which is 256, minus 4 times 3 times 16, which if you pop that into your calculator is 192, all divided by 2 times 3, which is 6. We can solve that a little bit more, so we end up with plus 16 plus or minus the square root of 64 divided by 6, and then we end up with plus 16, the square root of 64 is 8, so plus or minus 8, getting a bit keen there, plus or minus 8 divided by 6. So we have two possible answers here. We have plus 16 plus 8 divided by 6, and we have plus 16 minus 8 divided by 6. Now if we solve those, we come out with x is equal to 4 or x is equal to 1.33. We have two possible values. What on earth do we do with those? So I'm going to tidy up the screen. Sorry about that. We're going to tidy up the screen. So you can see here I've just got rid of everything, and we're going to go back to just our answer here, that x is equal to 4 moles or 1.33 moles, our two possible answers from the quadratic. And what we've got to do here is we have to look back at the ice table. So here's the ice table that we had at the start, just a bit neater than with my scribbly handwriting. And we said that at equilibrium there'd be 2 minus x moles of ethanol left, 2 minus x moles of ethanoic acid, and we'll make x moles of ethyl ethanoate and x moles of water. Now with our two possible answers, only one can be correct, and it's trial and error. Now if x was equal to 4, then at equilibrium we would have 2 minus 4 moles of ethanol. We would have minus 4 moles of ethanol. Now, you can't have minus moles or something. You've either got moles or you haven't. There's 0 or there's moles. So it can't possibly be 4 moles. It can't be that one. It's bigger. So if your mole value is bigger than x, it can't be that one. So this tells us that our x value has to be 1.33. And our question says, how much ethyl ethanoate will be formed? Well, ethyl ethanoate we said would be x. We've worked out our value of x, so the answer to our question is that 1.33 moles would be formed. And that's how we do those. So, activity 2. This is the same as what we just looked at. 2 moles of hydrogen were mixed with 2 moles of iodine and left to reach equilibrium. If the value of Kc for the reaction was 5, how many moles of each substance were left at equilibrium? If you're a bit confused, go back and watch the first example with the esterification again and the quadratic. If not, pause the video and see how you do. So the answer for activity 2 then. First of all, we need an equation. So this is one we've looked at before. We've got hydrogen gas reacting with iodine gas, forming 2 moles of hydrogen iodide. And we're going to make an ice table. So H2I2 and 2HI. And we've got here 2 moles of hydrogen mixed with 2 moles of iodine and left to reach equilibrium, and we've got Kc being 5. So 2 moles of hydrogen, I'm going to put 2 in the table initially, reacts with 2 moles of iodine, and we've got 0 moles then of the Hi at equilibrium, initially. At equilibrium, we haven't got any information, so we've got to look at this in terms of x. So H2, we're going to say, has gone down by x, and because it's a 1-to-1 ratio here with I2 is going to go down by x as well. Now it is a 2-to-1 ratio between Hi and H2, so if H2 has gone down by minus x, Hi has to go up by 2x, because minus x plus 2x is the 1-to-1-to-2 ratio that we have in our balanced chemical equation. So at equilibrium, we'd have 2 minus x moles of H2, we'd have 2 minus x moles of I2, and we would have 2x moles of Hi. Now our concentrations, we haven't been given a volume here, so we're going to use V. So concentration is going to be 2 minus x over V for H2, 2 minus x over V for I2, because moles over volume, and 2x over V for the Hi. So next thing we need to do is we've got to work out what our Kc expression is. We've done this before. So this is Hi in square brackets squared, because it's 2Hi in the question, divided by H2 times I2. And we can put our values in here. So we know that this is Kc is 5. So I put 5 there, and I'm going to put the numbers in. So Hi is 2x and it's squared, and that's divided by V, I should have put there, sorry about that, divided by 2 minus x over V for the concentration of H2, times by 2 minus x over V for the concentration of I2. Now, because of the squared on the top of the calculation here, we've actually got 2 minus V's, 2 divided by V's, 2 divided by V's on the top, and we have 2 divided by V's on the bottom. So they both cancel out, so we can simplify this to 5 for our Kc value, because the question tells us it's 5, equals, I've already got an equals there, I don't need that twice, so equals 2x squared, which would be 4x squared, because we square everything that's in the bracket. So we square the 2 and we square the x. That's going to be divided by 2 minus x times 2 minus x, and if we times out that bracket as we did before, etc., we have 4x squared on the top, and we have again 4 minus 4x plus x squared on the bottom. So as we did before, I'm going to just rearrange this. So everything that's on the bottom, I'm going to bring to the other side of the equal sign, and I'm going to times both sides by everything that's in the brackets I've just drawn. So we're going to have 5 times 4 minus 4x plus x squared, and that is going to be equal to 4x squared. So again, timesing that out, we would have 20 minus 20x plus 5x squared equals 4x squared. And then we're going to bring this 4x squared to the other side to make it equal to 0. So we're going to end up with 0 equals, or 5x squared minus 4x squared will be just 1x squared, minus 20x plus 20. And there's our quadratic. If we solve the quadratic, A, B, C, using the quadratic equation solver on the previous slide, which I'm not going to go through on this slide because it takes an age and you don't want to be sitting listening to me forever, but what we get are two values. We get that x is equal to 18.9 or x is equal to 1.06, and if we look at our ice table, it can't possibly be 18.9 because we only start with 2 moles of hydrogen, so there's no way that we can make 18.9 moles of hydrogen iodide, so, or 18.9 times 2 moles of hydrogen iodide, so definitely can't be that one. So this is our value of x. So how many moles of each substance were left at equilibrium? I'm going to change my pen colour just to make it clearer. Well, hydrogen is 2 minus x, so we'd have 2 minus 1.06, we'd have 0.94. We'd have the same number of moles of I2 because it is 2 minus x, and we'd have 2 times x. We'd have 2.12 moles of the hydrogen iodide. And that's how we'd solve that one. Now, there is some good news. As I've already said, you don't have to use any particular method to solve the quadratic. Once you have it in the form ax squared plus bx plus c equals 0, you can, well, it's not really cheating. All the exam board wants to see is that you know it's a quadratic and you can rearrange it into the quadratic formula. If you've got either of the two calculators on screen or any models above those, the calculator has a quadratic equation solver. So have a look at how to do that. That's what I did for the previous slide. Didn't need to use minus b plus or minus the square root of etc, etc. And just use the quadratic solver. That's all you need to worry about. Let me know if you need help working out how to do that with a quadratic solver, or if you need any more help with it.